All right, Chem 30, we are moving on to our third unit on equilibrium. Okay, this is out of chapter 15, what we're going to be going over today. Okay, but this unit is chapter 15 and 16, so we're looking at chapter 15, it's equilibrium systems, and then chapter 16 will focus more on acid-base systems. Okay, so kind of some preparation, some things you need to know. So again, dynamic equilibrium we've talked about before, okay, in different science classes, but it's just the balance between two opposing agents of change. Okay, there's no net change because the rates of the upward movement and downward movement are equal at any given moment. Okay, chemical systems at equilibrium have constant equilibrium properties. So scientists describe chemical systems in terms of empirical properties, so temperature, pressure, volume, and chemical amount. We talked about a lot of those before. Okay, and so when we're thinking about a chemical reaction or a chemical system at equilibrium, all of those are balanced out. It's not changing temperature, pressure, volume, or amount anymore. It's kind of reached that point where the forward reaction, reverse reaction are equal and opposite. Okay, the easiest way to study these systems is in a closed system. Okay, again, closed system means that matter cannot be exchanged, but energy can. Okay, so closed systems at equilibrium. Okay, so up till now we have assumed that the reactions are always spontaneous, rapid, quantitative, and stoichiometric. Okay, evidence obtained from many reactions contradicts. Oops, move this. So yeah, evidence from many reactions contradicts that reactions are always quantitative. Okay, so sometimes when you put two things together, okay, there still can be reactants present even after the reaction stops. So not all reactions, when you put them together, are going to be forward and all of the reactants used up to make products. A reverse reaction can occur according to a collision reaction theory. And so really when we're looking at these equilibrium, okay, so like for this one here, like, so this would be our reactants for the forward reaction, but then these are also already in our like solution. Okay, some of them are going to collide and make some more of these. So we have a forward and a reverse reaction. At equilibrium, the forward and reverse reaction are even. Okay, and some other examples. So like when the pressure on the equilibrium system changes, the equilibrium is disturbed. Okay, so like when you open a bottle, like a can of pop or anything like that, it's a closed system. When you open it, you change the type of system it is, and the equilibrium is disturbed. You get the bubbles coming out. Okay, another example. So according to the theory of dynamic equilibrium, as long as a container remains closed at constant temperature, the rate at which the molecules in the liquid state evaporate is equal to the rate at which molecules of the gas state condense. So basically for this, so you just put a lid on some water. Okay, we have some H2O gas up here, H2O liquid. They're going to be equal and opposite. And then another one here. So when you dissolve copper 2 sulfate at equilibrium, okay, again, if it's saturated, we get that sum in the bottom. We talked about that last year, is when we get the saturated solution, some of the dissolved solute, okay, it hits each other and becomes a solid, and then some of the solid becomes aqueous, and back and forth it goes. Okay, so some things that we can assume. So we assume that any closed chemical system with constant macroscopic properties, so basically if we can't see anything changing, okay, is that in a state of equilibrium. So we have three types. We have phase equilibrium. So this is where a single chemical substance exists in more than one phase in a closed system. So that would be like the water, where it can be a gas or a liquid, okay, with the lid on top. So it's equal and opposite. The solubility equilibrium. So a single chemical solute interacting with the solvent where excess solute is in contact with the saturated solution. So that would be the example of the copper 2 sulfate, that saturated solution. And then the chemical reaction equilibrium. This involves several substances, the reactants and products of a chemical reaction. So two general chemical processes that reach equilibrium are as follows. So one is a reaction with reactants and products in the same phase, such as a reaction between two gases to produce a gaseous product. So the equilibrium they reach is called a homogeneous equilibrium. So if they're all kind of in the same state. Okay, a reaction in which the reactants and products are in different phases, such as an aqueous solution of ions, in which the ions combine to produce a slightly soluble solid that forms our precipitate. Okay, this equilibrium they reach is a heterogeneous. Again, homo means the same, hetero means different. So homogeneous is all in the same states, heterogeneous would be in different states. Okay, all three types are explained by the theory of dynamic equilibrium. Okay, a balance between two opposite processes, okay, occurring at the same rate. Okay, when any equation is written with arrows to show that the change occurs both ways. Okay, so we have the left and right, the forward and left to right changes our forward reaction, so that's going this way, and then right to left is our reverse reaction going this way. So some conditions that apply to all equilibrium systems. So the fundamental requirement for equilibrium is that opposing changes must occur at the same rate. So both the physical and chemical changes can reach equilibrium. There are four conditions that apply, okay, to all equilibrium systems. So the first one is equilibrium is achieved in a reversible process when rates of opposing change are equal. So a double arrow indicates basically our forward and reverse reaction are happening equal and opposite. Okay, next one is the macroscopic or observable properties of a substance, okay, such as temperature, pressure, concentration, pH, they're all at equilibrium. Okay, and so nothing's changing. So when you first put like two things together, you get lots of change happening. Okay, and you can see that change happening. When they become at equilibrium is when that change stops. Okay, and then next three, equilibrium can only be reached in a closed system that is maintained at a constant temperature. Ideally, a system should be isolated, but again, it's really difficult to get that isolated system. Okay, equilibrium can be approached from either direction. The system remains at equilibrium as long as the container is unopened. Okay, note also small changes in the components of the system are sometimes negligible, so they don't really matter, and we'll talk about that more as we kind of go on. As a result, equilibrium principles can sometimes be applied in situations where the system is not physically closed. So some examples: in a solid in a saturated aqueous solution, you can neglect the small amount of water that vaporizes from the open beaker throughout the course of the experiment. All right, so the law of chemical equilibrium. Okay, so when the sample of dinitrogen tetraoxide is placed in a sealed flask, it will undergo the following reaction. So it turns into nitrogen dioxide, which is brown in color. Okay, the N2O4, okay, is colorless, and O2 is brown. So a small quantity of N2O4 is placed in a sealed flask at 100 degrees Celsius. The initial concentration of our nitrogen dioxide would be 0 because we're just putting the dinitrogen tetraoxide in the flask by itself. So the flask should be colorless. The initial rate of the forward reaction is relatively large, while the initial rate of the reverse reaction is 0 because there's no product. So there's no way to go in the reverse reaction. As reactions proceed, the rate of the forward reaction decreases because we start to lose some of our reactant, our N2O4. The rate of the reverse reaction then increases because the concentration of our nitrogen dioxide increases. The color of the gaseous mixture will darken until at equilibrium, the color stays constant. Okay, so that's when we know it's at equilibrium, is that we have something that a macroscopic property, so in this case color, it stays at equilibrium. Okay, so at equilibrium, the rate of the forward reaction is equal to the rate of reverse reaction, so no further change in relative amounts of N2O4 and NO2. So again, we put it in a reaction, there's really it's colorless, there's none of our NO2. As the reaction proceeds, we start producing some of the NO2. Okay, there's more as the reaction proceeds, and then after, like, we have to give it more time. The color hasn't changed now, so now we know this is at equilibrium. Okay, what's happening here? So this is our reactant. We put it in, so this would be our N2O4. As we put it in the system, some of it is turning into NO2. Okay, at equilibrium, these two amounts are equal. Or not equal, but these two amounts stay the same. So in a chemical system at equilibrium, there's constant ratio between the concentration of the products and concentration of the reactants. The constant ratio in the law of equilibrium depends only on the stoichiometry of the equilibrium. So the mathematical equation that describes chemical equilibrium uses the following. So one, it uses the product concentrations in the numerator and the reactant concentrations in the denominator. Each concentration term is raised to the power of the coefficient in the chemical equation, and then the terms are multiplied. Again, so this is the equation. We'll do some examples. I'll show you how to kind of use this equation because you'll need it for your assignment. So this, given the general equation, if we have these lowercase a, it would be the coefficient. So a, and then this would be just the or whatever the compound is. So we have A plus B equals C, or produces C plus D. Okay, that's our, and like again, A, B, C, and D, these ones here would be our coefficients. So the equilibrium constant, or Kc as we know it, okay, is equal to the concentration of our products, so the concentration of C raised to the power of our coefficient times D raised to the power of its coefficient divided by A times the power of its coefficient times B to the power of its coefficient. Okay, the subscript C on Kc reminds us that equilibrium constant is expressed in terms of molar concentration. Okay, and then this summarizes the equation of the equilibrium law. Okay, and so just kind of, it's good to have and know what that is. Okay, and again, where the square brackets represent concentration, so really you have the concentration of the products divided by the concentration of the reactants. Again, all raised to the power of their stoichiometric coefficient. So just whatever number you put in front to balance it. All right, we're going to do some sample problems. I'm going to do these, or actually this one's kind of done here for you. So the arrow got moved over here. We'll move it a bit. Okay, so write the equilibrium law expression for the reaction of nitrogen monoxide gas, okay, with oxygen gas. So you need to always have the balanced equation, and then you just have the concentration of your product raised to the power of its coefficient divided by the concentration of your reactants raised to their power of their coefficients, and then multiplied by each other. Okay, and if you're given the numbers, you could actually solve what is the Kc. If the equation were to be reversed, the equilibrium law expression would be the reciprocal, and the equilibrium constant would be the reciprocal. So again, the reciprocal means we just are flipping this. So then this would go on top, this would be on the bottom. If you're given the equilibrium constant, like if you're given Kc and you want to find the equilibrium constant for the reverse reaction, you just go 1 over Kc, and that would be your answer. So using the products over reactants results in a relationship of the numerical value of Kc and the forward extent of the equilibrium that is easier to visualize.